Hi, my name's Jeremy Greer. I'm one of the co-founders at Oumi, and today I'm going to show you how you can train Llama 4 using Oumi. So first, starting off, we've got the Oumi GitHub page here at github.com/OumiAI. If we scroll down towards the bottom of the GitHub, we can see a list of model recipes that are supported. So here is our Llama 4 Scouts instruct recipe. It has 17 billion active parameters, but it actually has 109 billion parameters. So while I'd like to be able to train this locally, I think we're going to have to do some bigger hardware. So let's go to this config and see what it tells us. So right at the top of the config, we can see Oumi distributed torch run. So this command tells you exactly what you need to run for training if you have a hardware platform that your Oumi library is installed in that you can directly utilize. Say if you were running on a VM in Google Cloud or Amazon AWS, and you happen to have, I don't know, 8 A100s on your machine. But most of us don't have that. So we're going to have to go with something a little bit different. Umi actually allows you to deploy jobs directly to the cloud. Right next to our train YAML, we have a GCP job YAML, and the command's really similar. Umi launch configs, and then the name of the config, and whatever name you want to give your cluster. So that's it for training, but let's see what changes we need to make locally. So I'm going over to VS Code now. And here I have the Umi repository loaded in my VS Code. And so what I'm going to do is I'm going to find those configs. So under configs, recipes, llama 4, sft, scout instruct full. So now those same configs that we saw earlier are located here. So we can open the train one and scroll up, and we can see the same config we saw before, and the GCP job one for when we want to train this in the cloud. So I'm one of the creators of the Halloumi model, and so my ideal use case is to go ahead and train another version of Halloumi, a hallucination detection model, built on top of Llama 4 instead of Llama 3, what it was originally based on. So what changes do I need to make to do that? Well, I've already made some of these changes here, so let's dive in and take a look at what they are and why I made them. So first, we have the difference between the original config in our repo and my config. First, I've changed the sequence length to 8192. This is because the datasets that I use for training go up to that length. In addition, I've also added the 4 datasets that I use to train Halloumi here. So I've added them as Hugging Face datasets, I've identified the training split, I've specified the path in Hugging Face to them, and I've also added some instruction and response templates. Now, so this allows you to train on the outputs only, which generally is beneficial for supervised fine tuning as it allows you to converge more quickly and produce a better model. So I've done this for all 4 datasets, and I've also specified the text with padding collator. This will just pad them into batches. And I've added a validation set, which will tell us how we're doing throughout the training job, particularly at the end. Now, as an example, I've also specified max steps 100. This will limit the number of steps to 100 batches, which is primarily just for time constraints. Um, I've also incorporated a batch size of 2, which the default right now is 1, but it seems like we can fit it. In addition, I've also changed the optimizer to AtomW torch views because it converges much better than stochastic gradient descent. Now, lastly, I've increased the learning rate because I've found that this learning rate works well for our data. I've adjusted the max grad norm to 10 to help try to limit the instability of the gradient throughout training and help prevent loss spikes. And I've set compile to false because for whatever reason for this model, it doesn't seem to be improving speed that much, but that may change over time. I've decreased the logging steps to 5, and this allows you to get results for training loss much more frequently. In addition, I've reduced the empty device cache steps down to 1 because I want the cache emptied relatively frequently for such a large model. In addition, I want to save the final model to disk. Lastly, I've modified FSDP to allow backward prefetch to do backward post. What this effectively does is it moves when the backward prefetch is happening to essentially cut down on the amount of memory the backward prefetch takes up when it's overlapped with the forward pass. Now, let's take a look at the GCP job to see what I changed. So I've specified the storage mount in my Google Cloud buckets to be the Oumi team's Google Cloud bucket. And I've also added this line to upgrade transformers. This is because the Scout models are very new and the Transformers library is being updated on a daily basis in an effort to fix a number of the issues that have come out since launch. Lastly, I've specified that we point directly to this config, and I've also created a directory inside of that bucket, which is where I'm going to write the final model. And so once training is done, we create that directory and then we copy the outputs from the training run and we move them over there. Now, what command do we need to run this? That's simple. Just the one at the top of the line, Oumi launch up -c. So we'll go ahead and copy that and paste it into your terminal. Assuming you're in the right Conda environment, you'll be good. Now, I've already run this before, so we can see here an in-progress training run using the above steps, and you can see the losses converging down. And we're actually getting pretty decent mean token accuracy. We're in the 91 to 93% range right now after only 60 steps. And there you have it. Now you have everything you need to know to train Llama 4 using Oumi. If you found this tutorial useful, or if you build something really cool, leave a comment in our Discord. It's open to everyone.